Hi, this is the film version, so to speak, of part 2, talking about phase. So, hopefully, you just watched part 1. Here's how part 1 ended. Now, if I've got this motion being described in terms of, hey, the position of some function at time is equal to a times the cosine of omega t, this number between these 2 points is the phase. Now, suppose, well, if I take some mass, move it to a position positive A, and let go, this equation tracks the motion perfectly. That's why we chose to start with cosine, because cosine of 0 is 1, so it starts when it's at full amplitude. But suppose you don't get to choose when time 0 in the universe, at least the universe of your problem, is. In this case, this works out great if we can choose time 0. If I can say time starts when I let go, which is a thing that you can define in many cases, then, hey, that works beautifully. But suppose that you either let go at some other time, or you walk into the room, oh, it's oscillating, darn it, I better start my watch now, and then find out, and then try and map that on. We can account for that. Let's use the simple case of saying, suppose or suppose we move the object to x is equal to minus a. In this case, instead of taking this and lifting it up until it's at one displacement a, suppose I stretch it out until it's at location negative a. And then we let go. What happens then? Okay. What happens then is that, well, if I look at this, say I want to draw this, it's going to look something it's going to start at negative a, move back through the origin up to a, and so on, out to forever. So it's going to behave exactly the same way as before, which is good, because the mass on a spring doesn't know when we're defining, time 0 to be. Notice that that's exactly what it would look like if I started right here. And let it go. The behavior out into infinity is exactly the same. The only difference is, so if the behavior is the same, I should be able to write it the same way. And I can. But I need to account for the fact that I'm not starting off at the right point. So I need to account for that by using some phase constant. Okay. I have this phase constant. Now, how do I find out what that is. In a number of cases, we can reason it through. But I'd rather do this the hard way and then save the reasoning through for when we're happily, deeply understanding what we're doing and just wish to coast. What I know is that in this case, I know that if this is acting like a cosine wave, no matter where it starts, I can track it as displacement is equal to a cosine omega t plus some phase constant. Well, what is that phase constant? Okay, at x is equal to 0, or t is equal to 0, x is equal to negative a. So let's just put it into this equation. T is equal to 0, x is equal to negative a, which is equal to a times the cosine of omega t, which is 0, plus the phase constant, or negative a is equal to a times the cosine of the phase constant, or I can divide both of these sides through by a. The cosine of the phase constant is negative 1, or the arc cosine, or the inverse cosine of negative 1, is equal to the phase constant. In this case, the phase constant turns out to be pi. So the correct equation for this is equal to, the position as a function of time is equal to the amplitude A times the cosine of omega t plus pi. And because this is the term inside the parentheses, the phase at this instant is equal to omega t plus pi. Now, there are examples. If you have questions, I'll provide these examples to you either as PowerPoint slides, where I've worked these things out, or, depending on how well these films are received, in this format, of examples with more complicated phase constants. And we'll run across this a little bit later. But keep in mind that in most cases, all right, pi, that's exactly opposite. In a lot of cases, that you might keep in mind that the arc cosine of a particular number gives you two possible results. You'll have to use reason to work out which one it is. Because, let's see. Right, so if I have an answer where, say, my phase constant is pi over 3, that's an angle of 60 degrees. But is it positive pi over 3 or negative pi over 3? Because though the cosine is positive in both of these quadrants, you don't immediately know that. You must use reason to figure that out. For right now, though, I just want to be able to I don't want to go chasing that particular rabbit at this particular moment, because this discussion is about the phase and the most basic understanding of the phase constant.